this, 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 and this were all caused by this brittle fracture. Events like these are rare, but invariably catastrophic, involving loss of life, property, and confidence. So just what causes brittle fracture, and how can it be avoided? Some ferrous materials are brittle in tension, torsion, and bending. Others, like mild steel, are ductile. But just how ductile? Well, that's easily quantified by tensile testing. Eventually, the tensile strength of the material is exceeded, so it ruptures. Permanent plastic deformation has taken place. The cross-sectional area has reduced, the specimen's longer and slimmer. But some steels don't behave in a ductile way. Take this notched specimen. The local stress at the root is high, so the material yields rapidly. But the stress elsewhere stays low. With no reduction of area, failure is instantaneous. There's no warning. Typically, a brittle crack travels at more than 1 kilometre a second. By introducing a notch, we've upset an evenly distributed stress regime. Imagine a tiny element of the material across the tip of the notch. In effect, we have a minute tensile specimen. Under free conditions, this would behave like a simple tensile specimen, but this element isn't free. Its ends are anchored in regions of low stress, while its centre lies in the highly stressed plastic zone. The notch produces large plastic strains, highly concentrated at the root and constrained by large regions of relatively undeformed material. The plastic material fails suddenly. No deformation, no warning, a brittle fracture. If the load's maintained, the crack extends to complete failure. Invariably, brittle fracture starts at a stress razor, a notch, a hole, a cover plate, or a lifting lug. The resistance of a material to brittle and ductile fracture is known as its fracture toughness, which can be quantified by, among others, the Sharpie test. The Sharpie test tells us the energy required to break a small standard specimen. It reflects the resistance to initiation and subsequent crack propagation. To avoid brittle fracture, a particular Sharpie impact energy is specified. Temperature is crucial, particularly in ferritic materials like structural steels. As the specimen is cooled, it takes less to break it. Brittle fracture occurs at low temperatures, and there's a transition to ductile failure, the relatively slow growth of a crack, at higher temperatures. The range of temperature where fracture changes from ductile to brittle is called the transition region. Above it, ductile fracture absorbs lots of energy. Below it, there's low energy absorption and a high risk of brittle fracture. The ductile to brittle transition can also be seen in tensile tests by measuring reduction in area. But this has limited practical application. Brittle fracture is more likely to occur in thick sections subjected to high rates of deformation. So we use big test pieces, representative of the real thing. The rate of loading also affects the transition temperature range. Full thickness specimens are used to determine critical conditions in structures subjected to lower rates of loading in another test method, the crack tip opening displacement. CTOD testing, as it's known, has the added advantage of providing quantitative data for use in floor assessment procedures. This rectangular section specimen features a sharp notch and a small fatigue crack. In other words, a sharp defect. The size of the opening of the slot before fracture is a measure of fracture ductility. Solid carbon dioxide is added for cooling. Separation is measured with a clip gauge. It's automatically plotted against the applied load. The crack faces move apart with negligible crack extension. The initial crack length is measured after the test, and we can also inspect the fracture faces. Test pieces come in several different shapes and sizes. The compact tension or CT specimen requires much less material than the bend test piece, but it's more expensive to make. Full-scale wide plate tests and biaxial tests have been used to confirm the design methodology. A full-size plate containing the defect is welded onto massive end beams, which transmit the load. The plate's temperature is measured using thermocouples. The load is ramped up slowly. Strain and crack tip opening displacements are recorded until brittle fracture occurs. It's TWI's expertise in fracture mechanics that has enabled it to contribute to the development of British Standard 7910 and 7448. In tests like these, the operating temperatures, the thickness and fracture toughness of the steel, the loading rate, the residual stresses, and of course the presence of defects are all key factors. So at the design stage, all these properties and parameters, particularly the service life operating conditions, must be known if steel structures are to be made safe from brittle fracture.